Okay, here we look at a sample problem about the RLC and the root mean square value. So here it says a series RLC circuit driven with ERMS frequency FD consists of a resistance R, ZL, and ZZ. What are the power factor cosine phi? Yeah, so actually this cosine phi is called the power factor. So if it has let's just say if cosine phi is maximized to be 1, if it is 1, then all the power are consumed by the loading, the resistive loading. And if phi is 90 degrees, then no power is consumed. Okay, so here, so the first step is to always write our Z is R plus J times, or maybe we can just write it as ZL plus ZZ. Okay, because this ZL and ZZ include the imaginary part, the imaginary number. Okay, so R is nothing but 200, and then plus JL is J80, and then JZ is negative J150. So this is actually J and then 80 minus 150. Okay, so it turns out to be 200 minus 70J or J70. Okay, so we just use the ohm as the SI unit, although it has an imaginary part, but still we only need to write ohm for the SI unit. Okay, so for the power factor, it is actually phi equals arctangent of negative 70 over 200. Okay, so this number is negative 19.3 degree. Okay, so this is the phase, not the power factor yet. The power factor is cosine of phi, which is a cosine of negative 19.1 degree. But of course, cosine is an even function. So no matter it is positive or negative, the value are the same. Okay, so cosine of negative 19.3 degree is 0.944. So this is the power factor. And also the phase constant. Okay, so this is the phase constant. Okay, so this is easy. You just need to calculate the impedance and then just divide the imaginary part by the real part, and then take the arctangent will be the phi, will be the phase, and then take cosine of this phase will be the power factor. And then what is the average power P average dissipate in the resistance? Okay, so here, first thing we can calculate the absolute value of C, which means the absolute value of 200 minus J70. Okay, so for the absolute value of the complex number, so we take the square of the real part and then take the square of the imaginary part, add them together and then take the square root. Okay, so this value is 211.9 ohm. Okay, so this is the absolute value of the impedance, and the P average will be ERMS square over absolute value of Z, and then multiplied by cosine of phi. So which is just like this is absolute value of V, absolute value of I, and then cosine of phi. But here we have ERMS. We also can get the absolute value of C easily. So we will use this expression. So ERMS is 120 square and then over 211.9, and then cosine of phi is nothing but 0.944 in the previous slide. Okay, so this number is 64.1 watt. 64.1 watt. Okay, so actually this is not so difficult, just only need to plug in the number to the equation. Okay, so for part C, what new capacitance is needed to maximize the P average if the other parameter of the circuit are not changed? Okay, actually in the previous slides, we don't actually tell you of what we should do to maximize the power consumption. The idea is that we need to make this cosine phi to be 1. The cosine phi to be 1, it will maximize the power consumption. How we can make it to be equal to 1, which means that the phi should be 0 degree. Phi should be 0 degree. If phi needs to be 0 degree, which means that the imaginary part should be 0, because here we see that. Yeah, we hope this to be 0, which means that this part should be 0, so that it can make phi to be 0. And then the voltage and the current will be in phase, and all the power will be consumed by the resistor. So the point is that the imaginary has to be 0, which means that here we need to maximize P average. We need to make ZZ new to be negative of ZL, which is negative J80 ohm. Okay, which means that we just replace the capacitor, so that the new impedance of the capacitor is this value, and then in that case, Z new will be 200 plus J, and then 80 minus 80, which is 200 ohm, which is a purely real number, 全实数。So in that case, what is the new capacitance? Okay, so this is Z new. This is Z new. So we know Z new is negative J80, which is negative J over omega C. Okay, so this is negative J, and then we have FD is 60 hertz, which means that omega is 120 pi, and then times C, which means that C is, okay, we can actually do the cancellation. Negative J and negative J can cancel. So finally, C is nothing but 1 over 80, and then times 120 pi. Okay, so this is 33.2 mu F. So we just need to change the capacitor to this value, and then the P average will be maximized. Okay, so which means that the impedance is reduced from negative J150 to negative J80, which means that the C need to increase. The original C should be smaller than this one, because here we have at least if you take the absolute value of ZZ, this number is larger than this one, which means that C, original C is smaller. Okay, So this is the final part of this chapter. Okay, it talks about transformer. Transformer is in Chinese is 变压器. Okay, so it says a transformer assumed to be ideal, make things much easier. If there are some energy loss in between, yeah, the model will be much more complicated. Okay, so a transformer is an iron core on which are wound a primary coil NP turns and a secondary coil. So you altogether have two turns. If the primary coil is connected across an AC generator, the primary and secondary voltage are related by this one. Vs equals Vp and then times Ns. Ns is the number of turns for the secondary coil, and the Np is the number of turns of the primary coil. So you can see on this figure. Okay, this is the source, and then this is the first turn. Okay, the first turn, the primary turn. So the primary turn is Np, and then the voltage across the primary turn is Vp. Of course, this is like a RMS value. Usually talk about a RMS value. This is also RMS value. And then for the secondary coil, we use VSNS to represent the voltage difference and also the number of turn. Here we have the loading resistance. This is a loading. Yeah, you may consider it is a machine or any electrical device to consume the power. Okay, so the transformer will try to convert the power from here to there. Depends on the so-called turn ratio. The turn ratio can be either Ns or N over Np or the reciprocal of it, or Np over Ns, either of it. It depends. Maybe in the textbook it will already define it properly. Okay, so it depends on the turn ratio. If you want to up-convert the voltage, then the number of turns of the secondary coil should be larger than the primary turn, and vice versa. Okay, so it says there are so-called energy transfer. You can simply imagine or suppose this is the electric generator, 发电机. Electric generator, just like in Macau, we have a CEM generator. So when the generator generate the voltage, it can be as high as hundreds of thousand volts, so even higher than the Pikachu. Yes, like 几十万伏. And then you need some transformer in different stage to down convert the voltage, so that in our home or in the normal use, we will use 220 volt in Macau. So this 220 volt is also an RMS value. So if you just multiply it by square root of 2, it is like a 300 and something volt, which is the peak value. Of course, in some of the other countries, or some of the other region, they may use a 110 volt. 110 volt for different region. But yeah, in Macau, Hong Kong, we are using 220 volt. Yeah. So what's the point? Why do not the electric generator just generate the voltage at 220 volt directly and then transfer? I will let you know later. But here the point is that, yeah, here it means that if you just move this down, it is like Vs over Vp equals Ns over Np. So which means that the voltage across the turn is proportional to the number of turns, which means that if the Ns is larger, then Vs is also larger. If Np is larger, and Vp is also larger. Of course, this is the EMF generate at the very beginning, and then you try to transfer. So yeah, usually this Vp is a given value, and then of course Ns and Np are also given, but also of course you can design the value you want, and then after Vp, Ns, and Np are fixed, then you can calculate Vs out, so that maybe this voltage is up converted or down converted. Okay, so for this figure, it looks like that Ns is larger than Np, which means that Vs is also larger than Vp. Okay, so this is the first condition. The first condition is the voltage. The voltage across the coil is proportional to the number of turns. And then there are second condition is the conservation of energy. Here we do not consider any consumption energy loss, because here we just assume the transformer is ideal. So we have the condition of conservation of energy. For the first turn, the total energy is Ip times Vp. And the secondary coil, the power is Is times Vs. So I times V, I times V. Okay, so in that case, you can just move, which means that we have a Ip over Is, which is Vs over Vp. Okay, or in other words, I and V are inversely proportional if Vp is larger, because we have a fixed total amount of energy. So if we have a larger V, we have a smaller P, or vice versa. So here, if we have Ip over Is, it is Vs over Vp. Okay, so they are inversely proportional. In that case, this is equal to Ns over Np, because V and N are proportional. V and N are proportional. I and V are inversely proportional. So we have Ip over Is equal to Ns over Np. So if you just move the terms over, you have a secondary term, the current of a secondary term equals Ip times Np over Ns. Okay. Okay, so finally, we still have another condition, which is like Vs over Is. Okay, we have Is, we have Ip. Okay, we still have Vs over Is to be out. Vs over Is equals out. Okay, so in that case, you can see this is so-called the R equivalent, which means that R equivalent is like Vp over Ip. We don't explicitly connect a resistance in the first coil, but as much as we have this condition, and also this condition, then Vp and Ip should have another ratio. So we can see Vp, Ip, you can just convert it to, let me see, Vp, Ip, let me see. Okay, so for this equation, for the first one, For the first one, you can just move ns over np to the other side. So which means that we have a vp equals vs times np over ns. And then we can just plug in this one here. So we have vs and then times np over ns. And then for ip, we also move the terms over, which means that we have ip equals is times ns over np, like this. And then we plug it here. So we have is times ns over np. Okay, so here we have vs over is, which is r. So first we have r, and then times np over ns over np. So altogether we have np over ns squared, which is actually this one. So the r equivalent means when you try to see what is the impedance we see at the input, which is like np over ns squared times r. So, but actually we only have r. We only have the r at the very end. This resistor only connected to the secondary coil. It does not really connect to the primary coil. But for the primary coil, the resistance you can see is multiplied by the turn ratio double. Okay, so you can regard this is a turn ratio. And we may call it the impedance matching. Impedance matching or impedance transformation. Impedance transformation. Okay, so yeah, so for this case, if np is smaller than ns, so for this you can see this is np, this is ns is clearly larger. So if ns is much larger than np, so what we can see in the primary coil is that the R equivalent is much smaller than R. It's much smaller than R. And actually in the electrical generator case, if you try to reduce the voltage, then yeah, at the input you can see the impedance is much higher. Okay, so yeah, this is something about the transformer. Let's see a sample problem. You will have more feeling about that. Okay, so this is a sample problem. It says a transformer only on a utility pro operate at Vp equals 6.5 kilovolt. So which means that it from the electrical generator, it already done convert to a few thousand K, so that it can transmit it to some of the small area. Okay, and then before entering your home, so near your home, maybe there are some other transformer to really down convert it to like here 120 volt or in account 220 volt. So why we need to do this? It has some benefit. Okay, let's see. After calculate some number, I can tell you what is the benefit there. Okay, so first, so it says on the primary side and supply electrical energy to a number of nearby houses as Vs, and both quantity measure are being RMS values. Assume an ideal step-down transformer, a purely resistive load, and a power factor of unity. What is the turn ratio Np over Ns of the transformer? Okay, so first, so this is easy to calculate Np over Ns, because we already have Vp and Vs, and number of turns are proportional to the voltage. So we have a Vp over Vs. So it is like 8.5. So it's like 8.5 times 10 to the third power over 120. So this is the turn ratio. And this number turns out to be 70.8. 70.8. Okay, because it is a ratio, so we don't have any SI unit. Okay, so this is simple. So for question B, the average rate of energy consumption or dissipation in the houses served by the transformer is 78 kilowatt. What are the RMS current in the primary and secondary of transformer? So here we don't consider any complex impedance. In the practical case, there may be some complex loading, but here we only consider the pure real loading to make things easier. Okay, so here it asks you what are the RMS current in the primary and secondary transformer. Okay, so IS equals P average over Vs. Okay, so because here we only consider the real loading, which means that cosine phi is 1 here for a real loading, real load. Yeah. So we just Of course we have a cosine phi in the denominator, but cosine phi is 1, so it's nothing. So this is 78 times 10 to the third power over 120 volt. So this is 658. And then for IP, it is nothing but P average over VP. Okay, so this is 78 times 10 to the third power over 8.5 times 10 to the third power, which is 9.28. Okay, so this is still easy. So you just need to use IS times Vs. I times V equals P average for a real loading. Okay, so finally, it asks you what is the resistance Rs in the secondary circuit, or what is the corresponding resistance in the primary circuit. Okay, so Rs is nothing but Vs over Is equals 120 over 650, which is 0.18 ohm. And then Rp is nothing but Vp over Ip equals 8.5 times 10 to the third power over 9.2, which is 926 ohm. Okay, so actually for this sample problem, all the calculations are easy. But what is the story behind all of this number? It is like suppose. So actually for this one, the circuit is something like you have a real RMS, which is like the power near your home before going into the transformer. Okay, so the circuit originally looked like this. Okay, so this is a transformer. And then this is the loading at your home. Okay, so this is RS. Okay, so maybe you can just define, this is a ground, this is a ground. Okay, so simply like this. Okay, so here we have something like NP to NS. And then here, just as we have calculate, this is 0.18 ohm. And then here it is 926 ohm. Okay, something like this. And VP over NP over NS is 70. 70 is 70.8. So this is the turn ratio. Okay, so let's try to imagine if we don't have this transformer, what will it be? It will be something like we want to generate VRMS directly go to your home and then we RMS, it shouldn't change anything at all. It shouldn't change anything at all. Okay, so what's the problem here? The problem is that, just say the problem generated is far away from your home. So if I just, or maybe, so actually this one is actually near your home. Near your home. We have a transformer. Okay, so near your home we have a should be, this part is near your home rather than that one. This is near your home. Okay, the transformer is near your home. There are some small stations near your home to down convert the voltage. And actually this is far away from you. It is far away from you. Far away from you. You don't really expect the electrical generator is near your home because it may generate some magnetic field or may generate some noise. You don't really like it. So this will be far away from your home. Okay, so if it is close to your home, then hopefully the impedance inside could be small, so that if it is in series with this RS, okay, so maybe this R is even, this RS is comparable to this one. And of course for this one, it is far away from your home, which means that even the conductor is good, but if it is far away from your home, the resistance of this wire, the resistance is proportional to L over A, of course. It is like equal to rho L over A. Okay, so A depends on how thick it is. But if it is thicker, then you need more material. And then this is the distance between the generator and the place near your home. So it might be large. Maybe it takes a few kilometers or even longer. Or maybe for larger country, it may be like tens of kilometers or even longer. So this L can be large. But if we have this power down conversion near your home, the impedance is small. The impedance is small. Okay, so if we just transfer the power from far away using a very low impedance, this R can be comparatively large to your resistance. Let's say if this is near 0.18 ohm, then many power will be consumed there, which means so there are many power loss there. But if we just place a transformer near your home, then for this part, the impedance here is quite high, which is hundreds of ohm. So even though the distance is long, maybe this resistance, just say this is 10 ohm, or if it's here, it is 10 ohm. For both cases, if we assume the total impedance is 10 ohm, then for this one, only 1% of the power is consumed in between. So maybe it's fine, but I'm not really sure about the number, but just let you know. If this is 926, this is 10, which means that 10 plus 926 under 10. This portion of power is consumed by this resistor. But here, if the total resistance is still 10 ohm, then 10 plus 0.18, and then 0.18. So almost all the power are consumed by this resistor. That's why we need to use the transformer. That's why we need to generate the power with a high voltage and then deliver to the different area, and then near your home, you use a transformer to down convert the voltage, and then you can use it. So up to there, the impedance can be low, but yeah, the distance is short, so yeah, we can really minimize the resistance between the power station, I mean the transformer near your home to really enter your home. Okay, so that's why we need this transformer for high voltage power transfer.